A dairy farmer notices that a large circular water trough near the barn has become rusty and now has a hole near the base. The hole is 0.25 meters below the level of the water that is in the tank. If the top of the trough is open to the atmosphere, what is the speed of the water as it leaves the hole? Okay, so here we've got a large circular water trough. So it looks something like this. And there's a hole that's 25 hundredths of a meter below the level of the water in the tank. So let's say that it's filled to like this level. Okay? So the hole right there, water comes spurting out of it, and that hole is 0.25 meters below the water level. Okay, if the top of the trough is open to the atmosphere, what is the speed of the water as it leaves the hole? Okay, this is going to be a Bernoulli's equation problem. So let's go ahead and look at Bernoulli's equation and then determine what variables we need to write down for our givens. Okay, so Bernoulli's equation says pressure at one spot, and I'm going to call this the top and the bottom instead of spot 1 and spot 2. So the pressure at the top plus 1/2 the density times the velocity at the top squared plus the density times the gravitational field constant times the height at the top is equal to the pressure at the bottom plus 1/2 the density times the velocity at the bottom squared plus the density times the gravitational field constant times the height at the bottom. Okay, so we've got our two sides. Now we can kind of see what givens do we need. So let's get information for the top, and then let's gather information for the bottom. So at the top, well, we're going to need to know the pressure at the top, and we're going to need to know the density, and we're going to need to know the velocity, and we're going to need to know the height. Okay, so the pressure at the top, well, it says it's open to the atmosphere, so the pressure right here is going to be the atmospheric pressure, which is 101,300 pascals. Okay, the density, well, this fluid is water, so we know the density of water, we need to memorize that, is 1,000 kilograms per cubic meter. The velocity at the top, and this is where it can get a little tricky. Some key words. All right, this is a large water trough, okay, and it's got a small little hole in it, okay? So think about this. You've got this big pool filled with water, okay, and you've got a little itsy-bitsy hole. You might look out there, and if you don't see the water spurting out the side, you might not even notice this water level's going down. Okay, and that's why we're going to say the velocity at the top is approximately 0, because it's not even really going to look like that water level's dropping. And then the height at the top, well, we usually say the lowest point is height of 0, so that means that the height up here is 0.25 meters. Now let's get the bottom information. Okay. Well, what are we going to need? We need to know the pressure at the bottom. We need to know the density. We need to know the velocity at the bottom, and that's actually what we're trying to find. So that's our find. And we need to know the height at the bottom. Okay, well, the pressure at the bottom, the pressure right here. This is open to the atmosphere. So again, it is going to be the atmospheric pressure. Now, you might be thinking, it's below. The depth here should be more pressure, and you're right. Right here, there's going to be more pressure. But since this is open to the atmosphere, it's atmospheric pressure right here, and that is why the water is spurting out, okay? Because this is all higher pressure area zones than what this is, so the water starts to pour out there, okay? But at that exact point, it's open to the atmosphere, so it's atmospheric pressure. Okay, the density, again, you need to memorize the density of water is 1,000 kilograms per cubic meter. And then the height at the bottom, well, we said that was 0. That we define that to be 0, so it's going to be 0 meters. Okay, now we're ready to go ahead, substitute in, and solve. So we have 101,300 pascals plus 1/2 1,000 times 0 squared plus 1,000 times 9.81 newtons per kilogram. We didn't even write that one down, but we've got that one memorized from before. Times the height at the top, which is 0.25 meters, is equal to 101,300 pascals plus 1/2 1,000 times the velocity at the bottom, that is what we're solving for, squared, plus 1,000 times 9.81 times the height at the bottom, which is 0. So we can start simplifying our terms. We've got 101,300 plus 0 plus, if we multiply all of that together, we're going to get 2,452.5 is equal to 101,300 plus 500 times the velocity at the bottom squared plus 0. Okay, now we could go ahead and add these two together, but I'm going to go ahead and just start solving from here, okay? I don't have any like terms really to combine over here, so I'm simply going to subtract 101,300. And that's why I didn't bother adding, because these two are going to cancel each other out. So after I added them and subtracted it, I would be back at 2,452.5 is equal to 500 times the velocity at the bottom squared, divide both sides by 500. 4.905 is equal to the velocity at the bottom squared. Don't forget to take the square root. The velocity at the bottom is 2.21 meters per second. So the water is spurting out there at 2.21 meters per second.